So what to talk about? We're going to take a look at this thing known as Hess's law. Now, when it comes to Hess's law is actually pretty fun. It's something that you are going to absolutely enjoy in this case. I've already taught it to a couple other sections, and they've kind of enjoyed it as well. Because when it comes to Hess's law is like a puzzle. Like you're putting together these pieces of the puzzle, and then ultimately you'll be able to figure out how much energy we can either release or absorb based upon a chemical reaction. So we'll talk about Hess's law today. Now, one of the things that's going to happen with the notes here is I'm going to read off some definitions. As I read these definitions off, you are going to sit there and be like, I do not understand a word you're saying with this definition. And then after that, I'm going to go to the next definition. And you're going to say, I don't understand that as well. The next one, you'll say the exact same thing. But eventually we'll get to this sample problem that I have sitting right here. It's already in your notes that we're going to take a look at. We're going to walk our way through that sample problem. After going through the sample problem, we're going to revisit each one of these definitions, and they're going to make sense. Sometimes you have to see it to appreciate it, to understand what the actual definition is stating. So I'm just going to read it off, and then once again, we'll do a sample problem and come right back to these things. So if you look at Hess's law simply states that if a reaction is carried out in a number of steps, the change in enthalpy, or the heat of reaction, for the overall reaction is the sum of the delta H's for each individual step. Makes no sense. The next one simply says that most chemical reactions occur in multiple steps. And these steps, when I see the whole entire picture, is called the reaction mechanism. Still, makes no sense. Each one of the reaction steps is simply referred to as an elementary step. Once again, I told you three things there, you're not going to understand it. Stay with me, here we go. And we'll come back to this one as well in a second. So basically what we have here is I got this chemical reaction, which of course we learned way back in the first semester, that if I have a hydrocarbon plus oxygen produces CO2 plus H2O, we said this is known as what sort of reaction? A combustion reaction, exactly. And if you look at it, we always said, hey, it produces CO2 gas plus H2O gas in this case. And we know it's exothermic because there's always that delta we used to put over here to imply that heat was being released. Well, one thing I didn't tell you way back in the first semester is that this reaction does not take place in one step. It is actually two reactions that make this overall reaction up. And basically what happens is the methane does react with oxygen. It produces CO2 gas, just like we saw right here. But the difference is it does not initially produce H2O as a vapor. It produces H2O as a liquid. But watch what's going to play out here. This reaction, when it does produce the CO2 plus the H2O as a liquid, it says, you know what? I'm also going to pump out there 890 kilojoules of energy. Remember, that's negative. I mean, it's exothermic. So we're releasing that. So I get this, and I get all of this heat coming off of this thing. Well, if you think about it, water itself is like, wait a second. I'm around all of this energy. And if you remember from last night's heating curve problem, we learned that the molar heat of vaporization, which is defined as the amount of energy required to take 1 mole of, in this case, a liquid, and convert it into a vapor. And if you remember, we said for water, it had a value. Once again, I'll always give this to you, but since you worked on it yesterday, maybe you might remember what the value happens to be. Does anybody remember what it was? 4.01. It was what?
Oh, wait, 40.7.
40.7. We said 40.7 kilojoules of energy could take liquid water and convert it over to a vapor. This thing is around 890 kilojoules of energy. That means, guess what this thing gets to see? It gets to see some of that energy in this case, and what it's going to do is to say, hey, I as a liquid, I'm going to go through my own separate process here of going from H2O liquid to H2O gas. And we said it costs 40.7 kilojoules of energy. But you got to be careful here, because I don't need 1 mole to go through this process. Can't we agree that I really need to take 2 moles of these things and push them over to the vapor in this case? So what I'm going to do here is I'm going to go in here and I'm going to multiply this thing by 2 and multiply by 2 and multiply this by 2. So I'm just simply saying, hey, we need roughly about 80 kilojoules. Well, if you think about it, what does this really mean? From the perspective of this overall reaction, because in a sense, and let me point one thing out, you're going to do this as a part of your homework assignment as well. 2 moles of liquid water was being produced, right? But that 2 moles of liquid water is now going to be consumed, because it's going to go over here and produce the actual vapor. If we have things that are on diagonals, and we'll see this kind of pop up as we solve problems, we're going to subtract them out. So 2 waters minus 2 waters, you're gone. Because in a sense, I'm never going to see the water. It's going to be produced, and in a millisecond, it's going to take the energy in, and it converts it to a vapor. That's why we use our Bunsen burner. We never see liquid water. It just really quickly takes the energy in. I'm right over here to the vapor in this case. So if I think about it, the first reaction is like, hey, I was going to kick out 890 kilojoules of energy. But when this reaction is said and done, I don't see all that energy, because some of the energy was used right here to convert the liquid water over to the vapor. Which means that if I look at it, my delta H for this reaction is really going to be equal to negative 890 kilojoules plus 2 times, in this case, the 40.7 kilojoules. And then when I go through and I solve it, it's going to say, yeah, unfortunately, you can't say you released all that. Some of it was used here, and you'll notice. In the notes in 1 second, I provide you with the actual answer of what it's going to be. But watch this. The cool thing about this is that once I subtract out my liquid waters, I'm going to take everything that's on the reactant side and drop it down. I'm going to end up with CH4 gas plus 2O2 gas going to produce, well, CO2 gas. These waters, once again, I subtracted those out, those gone. Plus, I got 2H2O as a vapor. Once I subtract out the things that are on opposite sides, I will get back, if I did everything correctly, which we'll see in a second, I'll show you how we're going to approach these problems. I will get back to the original reaction, and so long as I get back to the original reaction, then I know that, once again, this delta H is going to end up being correct. And if you look at the notes, I already provided you the actual answer that says, hey, yeah, you're not getting, once again, all 890 kilojoules. Instead, the net amount of energy you're getting is 809 kilojoules of energy being released here. So if we go back and we look at what the definition states, it says Hess's law. If a reaction is carried out in a number of steps, this is one step, this is another step. So I got multiple steps here. The delta H of the reaction, okay, the delta H of the reaction here is the sum of the delta H's for each individual steps. That's what I did. I summed those things together to figure out what the delta H is going to be in this case. This term right here, it says most chemical reactions occur in multiple steps, which are called the reaction mechanism. When I look at this whole entire picture, like all the different steps in what is this reaction, then that's actually known as looking at the reaction mechanism. I see the full picture. Each reaction step in the reaction mechanism is called an elementary step. That means that this reaction is just called an elementary step. This reaction is called an elementary step. I can say, hey, within this reaction mechanism, I got how many elementary steps? 2. That's it. That's all we're simply saying. See the full picture, reaction mechanism, each one elementary step. Hess's law simply says that, hey, the delta H of the reaction is just the summation of the individual elementary steps in this case. Now, right now, you don't see where we're going to go with this, but I'm going to show you in a second what we're going to do. But a couple of things just to point out, which you already know this. So what I'm about to show you in the next slide, you know. But there's some rules that we need when dealing with Hess's law. And these 2 rules that we're going to look at, once again, you already know them. The first rule simply says that if I have this, in this case, thermochemical equation, and I've got, hey, my delta H is equal to negative 285.5 kilojoules, which is exothermic. If I flip this thing around, what happens to this value? It becomes positive, right? Because if it's exothermic here, which kind of implies like, hey, my delta is on this side of the expression. When I flip it around, it now becomes endothermic, so we know we gotta just multiply it by -1. If we flip the equation, multiply by -1, so we get a positive 285.5 kilojoules. We already knew that. The second rule, you already showed me in the last problem. The second rule says that, hey, you know what? Maybe I've got, in this case, 1 mole of water, and it's breaking apart in the decomposition reaction. And I say, hey, you know, it's gonna cost me 285.5 kilojoules of energy. I gotta feed in this thing to break the water apart. Well, maybe I want 2 moles of water. Well, if I go 2 moles of water, then this will become 2. 2 divided by 2 is 1. I gotta multiply this thing by 2 as well. Whatever I do to the coefficients, I must do in this case to the change in enthalpy. Now, let's see what's gonna happen here. In your homework tonight, what you're going to get is something that looks like the following. I'm gonna give you a reaction such as this one here. I'm gonna ask you in this case, what is the delta H of the reaction? Now, what I'm gonna provide you with is I'm gonna provide you with, in this case, some elementary steps. Now, unlike the problem that we just saw, the first one, these elementary steps are not set up correctly. And it's gonna be on us to manipulate these elementary steps in a way in which we can figure out what the answer to this is gonna be. Now, if you pay attention, this is extremely easy. But I will tell you right now, if you do not pay attention, like I said, it is easy. It is not difficult at all. I have students who just, they love this. It's easy, I love this, there's nothing difficult about it. The students who don't love it is because they just didn't pay attention. And they're like, well, I don't understand. How did you know to flip that one? How did you know to multiply this coefficient? So just bear with me, just pay close attention here. So what I'm gonna do is I'm gonna go to my first elementary step. So I'm gonna look at this elementary step right here. And what I'm gonna do is compare this elementary step to this reaction I have right here. I'm just gonna compare those two. Now watch what's gonna happen here. All I'm looking for is I'm looking for something that this elementary step shares in common with this. Only those two share something in common, which means I am not going to choose oxygen. Oxygen appears in all three. I need something that only these two share in common, and it's going to end up being what? It's going to be what? SO2, right? Sulfur dioxide. So I'm going to go here, and look at that. Those two match up perfectly. I know what I need to do with this now. Because what I know is I want to manipulate these elementary steps to get, in this case, them to look like what's up here. And the way that I can do that is I'll say, hey, for you, this is not good. You don't belong on the reactant side. Technically, to get you to look like that, you need to be on the product side, right? Which means I'm gonna have to flip this one around, but better yet, besides just flipping it, that gets me close. What else must I also do here? Wait. I want this one to look like this one. I gotta divide by 2. So what I'm gonna do is I'm gonna flip this around. That way you will now end up on this side so you can look like that thing. I'm gonna divide it by 2 as well because then I'll get not 2 SO2s on this side, but just 1 SO2. So watch what's gonna happen. I'm gonna go here, I'm gonna flip it and divide everything by 2, come back up here, there we go. Which means if I flip it and divide everything by 2, I get SO3, in this case as a gas, going to produce SO2 gas, plus I get 1/2 O2 gas. My delta H that I have sitting right here is now -1, because I flipped it, times, in this case, -196 kilojoules divided by 2. So I'm done. I'm okay. Finished with this one. I'm gonna go down to this next one here. And now what I'm gonna do is I'm gonna compare this one to this one. And once again, I'm gonna look for just something that only these two share in common. And if you look at it, the thing that the two share in common would be what? Sulfur. And if you look at the sulfur is like, hey, look at me. At least I'm on the reactant side. I'm very close. What I need is to simply do what to this one here? Divide by 2. So that's exactly what I'm gonna do here. So I'm gonna go in and divide this thing by 2. So what do we end up with? We end up with something that looks like this here. Sulfur, solid, plus we end up getting 3/2 oxygen going to produce, in this case, sulfur trioxide as a gas, and my delta H here is just now going to be negative 790 kilojoules divided by 2. Now, this is the neat thing. You will know whether or not you manipulate these elementary steps correctly. How will you know? Because what you're going to do is you're going to go and find things that are on opposite sides, and you will subtract them out. I see one SO3 here, one SO3 right here, 1 minus 1, I canceled out. Right here, I see a sulfur. I don't see any sulfurs on the product side, so I'm just going to drop you down. The oxygen, look what's going on here. I got 3/2 oxygen minus 1/2 oxygen. That gives me 2/2, which I believe in math, that is 1. I get 1 oxygen on this side right here. Once again, 3/2 minus 1/2. Now, sometimes I have students say, well, how do I know to subtract this one from this one? It's easy. I can't have a negative in this case, so it's always got to be some positive, so I know the 1/2 has to be subtracted from, in this case, 3/2. Take care of my oxygen. On this side, that means the only thing left to fall down is the SO2, and if I get back the exact same reaction, I have manipulated these things correctly, and now I'm ready to just go in there and figure out what the delta H reaction is going to be, which is just summation of these values. I mean, sum together, you should get an answer, which I have here in the notes, is negative 297 kilojoules. Yes?
I have 2 questions. One, if like when you're subtracting them, if say like the sulfur also had fractions, but the first one, like the sulfur was bigger, can you mix and match what you subtract from each, like for the oxygen and sulfur?
No, I can only subtract in this case things, so I can't take this and subtract it. Is that what you're saying from the sulfur?
No, I'm saying like if there was an equation where like if there was another element that also had like a fraction, you have to subtract them, but it was like the opposite one was bigger than like the other, like it might.
So say this was flipped around and so the 3/2 is here and 1/2 is here. All right, just say, let's do this. Hold on one second, because I think there might be a problem that we'll look at that's going to address that. Because we got a couple of these problems here, and you'll see that sometimes we might have to add, sometimes it's subtract. So hold on, we'll get there.
And then also, did you multiply by -1 because you have to flip?
Exactly.
Okay.
I flipped it. And once again, when it comes to a nice homework assignment, if you just said, hey, that's positive, I'm perfectly fine. I like to kind of do things like this for a couple of reasons, especially sometimes I encourage students in honors to do it, because when you go off to college and your college professor teaches you Hess's law, he's going to zoom through this thing. I mean, they go through extremely quickly. And what's nice is if you can go back to your honors chemistry notes and you have these things that are sitting here, then you'll be like, oh, that -1 is because I flipped it there. Versus you just looking at the answer and seeing some number there and not realizing that, hey, it was this number. How in the world did it come out being this new number over here? So sometimes what you're doing is kind of helping yourself in the future in this case. All right, what we're gonna do is let's look at this problem right here and see if we can solve this one. So for this problem, let's see what's gonna go on here. So I got this original reaction. They want me to figure out, once again, what the delta H reaction is gonna be. So delta H of Rxn. So when I look at it, let's see what we got here. They give us, once again, a 2 elementary step process. And we gotta manipulate, once again, this thing to try to figure out what the delta H of this reaction is gonna end up being. So, what I'm gonna do, I'm gonna go right back to the first elementary step, and I will compare it to that original reaction here. So I'm comparing these two. And if I look at it, what do they share in common?
Fe2O3.
Exactly, Fe2O3. And if you look at it, the Fe2O3 says, hey, based upon me, I need to do what with this first elementary step?
Flip it.
You gotta just flip it, right? Now let me just point one thing out. Let's just say, I didn't see that one. Some of you might have said, oh, I see you. You and you are unique, because it's not found in the second one. It doesn't make a difference. Fe2 also says, hey, I don't belong on this side. I need to be flipped over as well. So long as you find one thing that is unique between the two, it will tell you how to handle that equation. So if I look at this equation here, I'm gonna go in and say, okay, well, yeah, clearly I need it on the product side. So I'm gonna get something like this here, 2Fe solid plus 3 CO2 gas is going to end up producing, in this case, Fe2O3 solid, plus we get 3 carbon monoxide. And for the delta H, we got delta H is equal to, we got -1 times -6.39 kilocalories. So we're done with the first one. On to the next elementary step. I gotta find something unique between these two. Let's see, what would it be? Oxygen. That is unique. Only between those two. And if you look at the oxygen, it tells you exactly. It says, hey, don't flip me, but just simply do what? Yeah, exactly, multiply by 3. So I'm gonna go in here and simply say that's 3 CO gas plus 3 halves O2 gas, going to produce, in this case, 3 CO2 gas. And then my delta H over here is just gonna be equal to 3 times, and we got there, times -67.63 kilocalories. Now once again, I'm gonna go in here and confirm that I did this correctly. If I did, I better get back that original reaction. If I look at it, subtracting things that are on opposite sides, I got 3 COs here, subtract from 3 COs, you're out. 3 CO2s here, 3 CO2s here, you're out as well. Which means what's gonna drop down is 2 Fe solid plus 3 halves O2. Going to produce Fe2O3 solid, and my delta H, once again, of the reaction, is just the summation of these delta H's right here. And when you solve it, you should get the answer that I have here in the notes, which is going to end up giving us negative, there we go, 195.6 kilocalories. 96.5. There you go. All right. What I'm going to have you do is I'm now going to give you this problem right here. This problem has, in Spanish, uno, dos, 3. It has 3 there. So we got uno, dos, tres. So you got 3 elementary steps, and you got to kind of go in here and try to see if you can manipulate it and figure out what the delta H reaction is going to be for this problem. Remember, take it one step at a time. Then after going one step at a time and figuring out the thing that's unique between each elementary step, things that are on the opposite sides, subtract out. If they happen to be on the same side, then you'll add them together. This one here. And as you're working on it, I'm going to write the answer up on the board. And then once you're finished, take a look at it and see if you got the same answer. All right. Hopefully you got these three here correct. Now I just want to show you how the oxygen kind of got subtracted out. On this side, I have 2 oxygens. On this side, I have an additional half of oxygen. So on the reactant side, I got 2 plus 1/2. And if we go with 2 plus 1/2, I know that, hey, if I'm going to add, in this case, a fraction to a number, I gotta have what? From math?
Common denominator.
That's exactly it. Which means we're gonna need something like 4 over 2 plus 1/2, which equals 5/2. I got 5/2 oxygen on this side over here, and I got 5/2 on this side. They subtract out. And once again, what drops down is gonna be everything that reflects the original reaction, which means I know for a fact I did this correctly. Questions here. So if they're on the same side, you add them, opposite sides, you subtract. So tonight's homework assignment, it's gonna tell you on ΔHrxn that you're gonna go to the worksheet packet.